Unmute. Yeah, I can unmute now.
Good evening, and welcome to the fourth session of this FDP on quantum edge intelligence, organized by the Computer Science and Engineering Department of MCKV Institute of Engineering. We are honored to have Dr. Tanushyam Chattopadhya among us as the resource person of this session. Dr. Tanushyam Chattopadhya currently serves as the practice head at Sirius Digitech, a multinational joint venture between Adani and International Holding Company, bringing 23 years of experience in artificial intelligence. His responsibilities encompass strategic planning, product innovation, stakeholder management, go-to-market strategy partnerships, intellectual property coordination, and fostering university collaborations for the Adani Group. With a demonstrated history of leading cross-functional teams in the design, development, and deployment of computer vision and generative AI products, Dr. Chattopadhya has been granted over 100 patents. Recognized as a thought leader in AI and Gen AI, he has delivered tutorials and keynote addresses. He has served as a reviewer, technical program chair, and session chair at numerous international conferences and journals. He is also the author of a book and several book chapters and has published more than 70 papers in peer-reviewed journals and conferences. Dr. Chattopadhya graduated with honors in physics from Vishwa Bharati, securing third rank. He received the University Gold Medal for his MCA from Shibpur IIEST in 2002. He began his career as a researcher at the Indian Statistical Institute, Kolkata, before joining Tata Consultancy Services Limited in 2004 as a principal scientist, a role he held until November 2022. In 2012, he was awarded a PhD from Jadavpur University for his research conducted at ISI Kolkata. He has received advanced training in speech signal processing from IISc Bangalore, image processing from IIT Kharagpur, and video processing from IIT Delhi. He was awarded the Computer Society of India Young IT Professional Award. He received the Significant Contribution Award from CSI for 2012 and 2013. He has received the Best Paper Award many times. He excels at bridging academic research in AI with practical product development. Once again, welcome everyone to this FDP organized by Computer Science and Engineering Department of MCKVIE Institute of Engineering. I request sir to kindly enlighten us with his knowledge.
I believe I'm audible.
Yes, sir.
Yes,
You are
sir.
And
audible.
my screen is also visible.
Yes, sir, it is visible.
Done? Okay, so let me now, with all these things, I can start. So I prefer to start from here. Can you see my folder?
Yes, sir.
Okay. So, I mean, what I prefer is that before starting my presentation, let me open all the cards to you. Means these are the papers based on which I have prepared the slide decks. Okay. So it varies from the, I mean, last almost 1 year back, most of the papers you can see downloaded last 1 year back almost. So what I'll start with, so this is something, I mean, it's a quick reference and notes for you. So Gartner is something for the business purpose. So this is something, one slide deck, I mean, I have used in it. So value in quantum computing optimization. This is the slide deck taken from Gartner. I'll take you through all these things, okay? Second one, this is a October 2023 paper. You can take a note of it. So this is the main thing, whatever I'm going to cover here. It's a survey on quantum machine learning, current trends, challenges, opportunities, and road ahead. My slides will evolve only, I mean, mostly on these. Another very good paper is here. So this is something that quantum machine learning beyond kernel method. It was published in Nature. And another article is ICML, International Conference on Machine Learning, possibly aware of the conference. So it is 2021 paper, I believe. Yeah, by Wang et al. Quantum algorithms for reinforcement learning with a generative model. So with this, I set the context that I am not going to tell you anything disruptive or anything very, I mean, what I can say, that very unique things that only I can say. So everything, whatever I'm going to cover here is based on these papers and these openly available resources. Or,
Sir,
yeah,
excuse me. Would you kindly just switch on your video once? We will just take a
I
snapshot.
could not do it. So I tried. So yes, now it's possible.
Oh,
I tried.
okay,
Earlier,
okay,
it
sir.
was not allowed. I was not allowed.
Okay, sir.
So this is from my, I mean, guest house, company guest house. I'm in Ahmedabad
Okay.
now.
Uh,
Okay. So I believe I mean, my face, my presentation is visible and I'm audible. So today's fourth day, still before going. So just, I mean, how I oriented, I mean, how I organized the slides today. I definitely, I mean,
This got disconnected.
Let us wait for him.
uh, I believe that I'm audible again. I lost in between.
Yes, sir.
Yeah, please allow me to share screens. I'm switching off the camera. I mean, maybe because of so many bandwidth issue came. That's why let me switch off the camera. Okay. So
Okay, sir.
I believe my screen is there visible again.
Yes, sir, it is visible.
Yes, sir.
Thank you. So quantum computing fundamental. So how I'm going to say is that I'll cover that. I'm not covering what first I mentioned that what are the basic documents on which I prepared my presentation. Second one is that what I'm not going to cover, because in quantum computing, most widely covered topic is that how the security will impact in the post-quantum era. That's why I'm not going to speak anything about the security aspects. So what I'm going to speak here today, mostly that what are the differences in traditional classical computing and quantum computing, be it in storage, be it in computing. And second is that how machine learning algorithms will change once the quantum computing will be in place. So first, let me start with these, that the limitations of the classical computing. Why people need to think, means for me, it is the motivation why we need to think of that. I mean, what is the motivation for taking that quantum computing? So classical computing faces physical limits in transistor scaling. Whenever I'm telling it, I usually, I mean, request faculties to remember that whatever you are teaching in your class, one of them is the Moore's law and the Crider's law, isn't? So what Moore's law told that the semiconductor computation will be double in 5 years or 10 years. I mean, exactly, I cannot remember. You can correct me. So even after that, till 1970 to 2000, it worked. But after that, it is not happening like this. So classical computing facing a serious limit in transistor scaling, causing performance bottlenecks and slow the progress in large machine learning models. So one example of such large machine learning model everyone knows is that large language model. Anyway, I am making all the images, whatever the images you can see in my slide are all built using large language models. I am using some, some GPT, not GPT actually, I'm using Copilot to construct the slides. Next one is the high computational demands for machine learning. So first one is the, limitation of the classical computing. Now coming that how the machine learning is advancing today. Till 2017, before the paper by Vashwani et al. Came, is that attention, what you want or all you want. Exactly paper title, I believe that you can understand which paper I'm referring to, the attention model. Till that time, that, computational demand was somehow mitigated by the, existing transistors. But for the large language models, one such examples you are aware of possibly is that Bharat GPT, whatever is, Government of India's initiative. So for that, if we want to really make some GPT, general purpose transformer, first question comes that where you can execute it. So first I told that the limitation of the classical computing is that classical computing cannot go beyond up to a certain limit. Whereas high computational demands of machine learning, that's why it cannot be mitigated using the classical computing devices. Now, what is the promise of quantum computing? Quantum computing leverages quantum machines to significantly enhance computation efficiency and solve complex problems. What are those complex problems? One example of such complex problem is that quantum machine learning. Quantum computing applied to machine learning creates quantum machine learning systems with new algorithms and hardware. I am not going to any details about it. With the help of new hardware, we can go for new algorithms. Is there anyone who used, machine learning? You can unmute and say that, yes, I have used machine learning algorithm using ELO. Is there anyone? I want to meet. I know it's a web session, but still I want to make it a bit interactive. Otherwise, I'll feel that I'm talking for 1.5 hours and you are sitting idle, or you are searching your mobile phone. So is there anyone in the audience who used ELO model for image processing? You can unmute. Is it allowed? If not, you can write in the chat.
It is allowed, sir.
Okay. So anyone used yellow model or any such, model for computer vision or any
Yes, sir. We have.
animation
Yes, sir.
you have done? Okay.
Yes, sir.
So I cannot see you, but if you have done, so do you know that is it possible to deploy on an Android mobile phone the same version? The answer is no.
Same version is not deployable.
Yes. The reason is that the
High computational cost.
model size is one impact.
Right.
So normally what happens, that model, whatever is using PyTorch has been built. You see, whenever I'm talking, I'm expecting that you know classical computing and classical machine learning. That is the basic assumption on which I start this presentation on quantum computing. So whenever you are building the model, in classical, on yellow like structure, yellow is based on PyTorch. So extension comes as a .pt. Now this PT cannot be hosted on an Android application. You need to convert it to the .wnx format. So whenever we are converting to the wnx format, it is reducing the size of the model significantly. Any 20 MB model can come to 8 MB immediately. How this thing happens? The quantization means whenever we are talking about machine learning is nothing but so in machine learning, the model files are storing the weights. So you know that in a CNN or RNN, we are building some neural networks where each neuron is assigned to some weight. And these weights are stored in the model files. Now, if we reduce the number of bits to store this to store these numbers, it impacts a bit in the accuracy, but model size significantly reduces. So, why we need to do it? For that means whenever I'm talking about this, so what we are doing, for every data, we need to do some quantization. Means we are assuming that it is a continuous distribution. We know that it's a continuous distribution, but for our computing purpose, we are discreting it. We are getting the discrete by quantizing it. Now, in quantum computing, it is something that you see written here is the quantum computing applied to machine learning creates quantum machine learning systems with new algorithms and hardware. So most of the new algorithms are coming with the assumption of that it can support some continuous distribution instead of the discrete distribution. So whatever the Hilbert space transformations you can see, we can convert it to some corresponding transformation in the continuous domain if we have the quantum computer in my hand. So I believe that the fundamental concepts of qubit and superposition and block sphere is already covered. If it is covered, please tell me so that I can move to the next slide. Is it covered already? What is qubit? What is qubit superposition? No comment came, so let me
Yes, sir,
cover.
it is covered. Yesterday it was covered.
Yeah, I know that it should be. So let me come here. That's single qubit superposition and two qubit superposition. What is single qubit superposition and what is two qubit superposition? So single qubit superposition states show probabilities from fully from 0 to 1 with various intermediate values. So whenever we are identifying some weights or giving some probability score, that is, you know that entire machine learning is coming something like that, that whenever we are returning something, we are returning some probability values. Now for each of the probability values residing in the range of 0 to 1, what happens that whenever we are presenting the probability values, we are storing it in some, it requires number of bits, whereas a single qubit can hold the probability value. That's a big change in the paradigm. Second, Max-Born rule requires the amplitude squares to sum to 1, ensuring probabilities are normalized in the quantum states. So whenever we are getting the probability values, we have to square their amplitudes. You all about the root mean square, error, and all these things you know. So you can understand what it is. It is that the amplitude square should sum to 1. Means whatever be the probability, if it is residing in the 0 to 1, maybe 0.5 plus 0.5. So square of this 0.5 square plus 0.5 square should come to 1. So this is something that Max-Born rule. And what is the two qubit superposition? Two qubit systems exist in 4 superposition states with amplitude relating to the probability of the final states. Classical versus quantum systems. So classical systems determine definite states sequentially. Quantum systems produce probabilistic distribution of states. So whenever we are thinking of the states, so the states are deterministic in classical, whereas the quantum system produces probabilistic distribution of the states. So the states itself are probabilistic distribution is available. That's why we can store more amount of data. Now coming to the quantum processing part. Okay. So classical versus quantum system. All of my slides are, going like this, that classical versus quantum. Everything is, phrased like this. Okay. So classic, because so that you can find the analogy how you are doing now. Otherwise, if you forget that how you are doing it now, you cannot map it very well in how it to be done. And you can easily understand whether you are using it and how you need to change your practice if quantum comes. It definitely will come maybe in 3 to 4 years. Okay. Classical systems find solutions sequentially, whereas quantum provide probability distribution of states. I completed there. Next one is the quantum gates the reversible unitary operations, forming circuits that perform quantum algorithms on qubit. So right now, digital logic, whatever we heard from or we learned from the Maurice Banner books and everything is that XOR, NOR, what are the other gates? That exclusive OR, NOR, NAND, all these gates are there. Using this, we are trying to do something. Quantum gates are reversible unitary operators. So forming circuits that are performed on quantum algorithms on qubits means these gates can work on the qubits. Present algorithms are working on the XOR and NAND are working on the Boolean values. Boolean values mean 0 to 1, which works using AND and NAND, NAND and other gates, whereas the quantum gates can work on the qubits. What is quantum entanglement? Entanglement like particles so changes in one affect the other instantly, enabling quantum correlations. Means here that you know that one affect the other instantly and enabling the quantum correlation can be identified. Right now what we are doing entanglement for that for the module cellular automata and all these use cases, sorry, all solving all these problems. So here in using the quantum correlations is not the normal correlation coefficient. We can use the quantum correlation which will work on the qubit. Quantum decoherence and noise. So we need to do noise clearing and decoherence. Decoherence and environmental noise disrupt qubit stability, posing challenges to reliable quantum computing. This is the major challenge of why we have not yet received that proper quantum computing on which we can start running our codes. So you can see here that disrupt the qubit stability means environmental noise can disrupt the qubit stability. That is the one of the biggest challenge. What is the showstoppers of taking the quantum machines in the reality? So how we can do this error corrections? One is the NISQ error overview. Near-term quantum processors support 50 to 100 qubits, but lack full fault tolerance. Means up to 50 to 100 qubits are supported quantum processors. Near-term means whatever is available, but but lack in full fault tolerance and enabling hybrid algorithms in various fields. So we cannot directly use the classical or nor we can go for that, fully the quantum, algorithms. We need to go for the hybrid algorithms. Quantum error correction, QEC, spreads information across entangled qubits to detect and reduce errors like bit flips and phase errors despite the no cloning theorem. So I believe that someone has mentioned about the no cloning theorem is one of the basic theorems what is used here. So next, coming to the physical error threshold. Current quantum systems have physical error rates above ideal thresholds, but improvements are expected within 5 to 10 years of the fault tolerance. That's why I told that in sitting in 25, I can see that by 29, 27 to 29, we can get some quantum computer. But for the foolproof, the fault tolerance, we are expecting another 5 to 10 years. Actually, by 2030, we can expect something full fault tolerant system. Quantum error mitigation reduces the error during computation without fully removing the noise. So in last slide, I was mentioning that environmental noise will impact the stability of the quantum computer, but the QEM, quantum error mitigation, reduces the error, not removes the error, reduces the errors during computation without fully removing the noise, offering easier implementation but less qubit protection than the QEC. QEC is the quantum error correction. Coming to the next slide, quantum stack, abstraction layer from hardware to the applications. Sorry. NISQ error challenge. NISQ devices have small quantum circuits affected by noise, limiting error corrections implementations. So, I started with quantum, classical versus quantum, and some challenges I mentioned. One is that error and the stability issue, and then I came to that how these errors are used now. So, our errors are to be removed now. So, NISQ devices have small quantum circuits affected by noise, limiting error correction implementation. fault tolerant quantum computing, fault tolerance ensures quantum system operate reliably despite hardware or software failures. So this is very important, the fault tolerant quantum computing. This is something we need to achieve, but we have not yet fully reliable systems we have achieved so far. Quantum stack layers, though lots of algorithms we can see published by, enormous authors, where it's an ideal situation if we get this, how it would look like. But I'm telling you what is in the reality, that quantum stack abstraction layer from hardware, how it is there. So quantum stack layers. So quantum computing stack includes hardware, microarchitecture, compiler, programming languages, and algorithms. Like it is different from, you can understand from the the von Neumann architecture. So quantum computing is in hardware, microarchitecture, what is present here, compiler, it's also here, and programming languages. And the variants, the realistic quantum hardware using superconducting, that seeds the coming from the concept of physics, superconductor. You possibly aware of the term the supercomputer, and ion-trapped quantum dots and neutral atom qubits. These are the four variants: superconductors, ion-trapped quantum dots, and neutral atom qubits. For the superconductors and all these things are very much unstable in nature. So if my make itself, or using which I'm trying to make the quantum computer, if itself is not stable, the quantum, entire system is become very much unstable. First, the dimension reduction. Whenever I'm talking about the classical dimension reduction techniques, which one comes to your mind? Any one or two you can speak about. Please unmute and speak. I mentioned it here. I know it's a, web session. So, most of the, if I ask it in most of the sessions, people are coming out the principal component analysis. So principal component analysis is a dimension reduction techniques. So quantum dimension reduction techniques also includes PCA and Q ladder, project high dimension data into lower dimension efficiently. So one work I have found, what is, recently in 2024 or 2025, I found one literature where people are telling that how that UMAP and TSNE, T-stochastic neighborhood estimation, and the uniform manifold and approximation projections, mathematical backgrounds can be modified to a quantum era. Next come the quantum supremacy explains. The quantum supremacy refers to quantum devices solving problems infeasible for classical computers within practical time frames. So it is very important factor here that the time complexity, that the execution speed is so fast, that is telling that practical time frames, if classical computer cannot do something, that is feasible in case of quantum devices. Quantum computing complexity, quantum complexity theory, it's another, another field is evolving, that the quantum computing complexity. We all coming from the computer science, it's organized by quantum computer science background faculties, I believe. So whoever has, you are possibly, some of you are teaching these algorithms for Coreman or other books. So you know that we are talking about the algorithm complexity. But quantum complexity theory extends classical models to include bounded error quantum polynomial time problems beyond classical capability. So whatever the, a traveling salesman problem, or the, other some traveling salesman program, and some other, that, hello?
হোক না হোক আলাদা ব্যাপার, বাট চেষ্টা করা ভালো, তাই না?
Participant, please mute yourself. Kindly mute yourself.
Okay. I thought that someone is asking some questions. No issue. So that is something my anticipation was that I mean some other calls will come and some WhatsApp message will come while I'm speaking here. So quantum complexity theory extends classical models to include bounded error quantum polynomial time problems beyond classical capability. So whatever the traveling salesman problem, some other some non-polynomial, what have the polynomial complexity means that which cannot be solved using polynomial times, that some of those problems can be solved here. And that's why I specifically mentioned at the beginning that I am not using the example of the quantum, post-quantum security, because security algorithms, it is based on the assumption that we know the algorithm that what is used for the security, but we cannot break it within this time limit. Okay. Next comes the qubit and superposition. Qubits utilize superposition, allowing simultaneous 0 and 1 states, unlike classical bits. So in classical computing, it is either 0 or 1. Here, it is simultaneously 0 and 1 depending on the probability. We can use it for the superposition is allowed in quantum. So I mentioned it 2-3 times possibly. That is something important. So now for the large scale infrastructure industry roadmap, as I am from industry, possibly most of the people are interested to, I mean, listen what is going to happen in industry. Roadmaps from leading companies outline milestone to achieve large scale quantum systems by 2030. That's why I mentioned by 27 to 2029, we should be ready to embrace the quantum algorithms, quantum computers. For that, certain features, certain algorithms I mentioned. One is the security, one is the machine learning, and out of machine learning, one is the dimension reduction techniques. We can start thinking, or we can start to research that how will it be modified in the post-quantum era. Quantum computing for the infrastructure, quantum computing offers new optimization methods, solving problems impossible for classical computers. Means it offers new optimization methods solving the problems impossible. So optimization, I mentioned one is the one problem solved, a statement I mentioned is the traveling salesman problem, or anything that is not doable in polynomial time, is a non-polynomial, is coming to the polynomial order of complexity. Similar one such problem is the complex optimization problem. Just before this session starts, I was working on one such very complex optimization problem where in a gas pipeline, so I'm sorry, for the CNG stations, how the gas should come and how many vehicle can come, it starts from the port itself. That sometimes some fuels are coming from ports, which is to be distributed to the CNG stations or maybe from the mines and to be distributed. And it should anticipate that how much passenger can come, how much customer can come, so that we can optimally use it. So it's a very complex optimization problem. What we can foresee to be use cases in post-quantum era. Categories of the quantum machine learning approaches, QML algorithms are categorized by classical or quantum data and processor types into 4 main groups. Parameterized quantum circuits, PQC, parameterized quantum circuits are enabled utilizing existing quantum computers with trainable parameters for optimized quantum algorithm. So here again comes that I mentioned about optimization. I mentioned about the machine learning algorithm. Parametric machine learning you all are aware of. So parameters for optimized quantum algorithms is the another area. So quantum computing complexities, theory and problems, whenever classical quantum complexity classes. So classical complexity problems include the polynomial, non-polynomial, NP-hard and the NP-complete classes. I mentioned about all these things in the last slide. So if you can map it with the book by Papadimitriou, Theory of Computation, or from the Core Man. So this is something that in the post-quantum era, the quantum complexity class of the BQP class represent the problem efficiently solvable by quantum computers using quantum machines principles like superposition. Superposition means that the same qubit is used for 0 and 1. Quantum superposition of qubits. Qubits can hold 0 and 1 stages simultaneously through superposition, unlike classical bits, where explicitly it is 0 or 1. And promise problems in the complexity. Promise problems have predefined inputs, constraints, and and are assigned to specific complexity classes based on the input characteristics. Yes. So quantum machine learning approaches. This is something my comfort zone, because machine learning is something I'm working on. And we are planning to move to quantum machine learning, because I mentioned that by 27, 29 first set come, and by 2030, maybe industry will see the changes. So you can see that right now AI has disrupted the business. Lots of layoffs are happening from the service companies. But what I see that it may be changed again, lots of requirements, because I believe that as a faculty, you are answerable that how many placement will happen in future. So I believe that this is a nice thing. What may again require to onboard lots of resources, because quantum computing compatible machine learning known resources are hardly, and that's why possibly you are the faculties, leading faculties who thought that to start learning on that. So for the quantum machine learning approaches include fully quantum, hybrid quantum, classical, and hybrid of quantum and classical, and parameterized quantum circuits for various data processing types. So fully quantum is something where the fully and this is something the hybrid of quantum and classical. Still now, I have, other than the next, the paper I mentioned about the International Conference on Machine Learning published in 21, I have seen most of the algorithms are the hybrid of quantum classical. Whatever I have seen, I'm not sure that, you may find some, because this is so emerging field that you can find some papers, what is published, but I have not noticed it. So optimization problems aim to find the best solutions which can be discrete or continuous, single or multi-objective in nature. I spoke something about the continuous and the discrete distribution. So most of the optimization problems are now using the discrete distribution. That's why I mentioned that whenever we are getting the data, we are quantizing it to certain, quantized level. And in the discrete distribution, we are treating it as to solve the problem. Optimization techniques are used on the discrete data. So in a classic quantum hybrid approach, we can use both discrete and continuous. If you want to move fully to the continuous, you can go to the quantum machine learning approaches, fully quantum. Or another is the, another was the parameterized, means that you know that the distribution estimation, where I can give the simplest example, maybe the Gaussian distribution, where any data distribution is estimated, and we can represent it as a mu and sigma, two parameters, mean and the standard deviation. So parameterized quantum machine learning is also, quantum circuits is also available. And I believe you know what is single and multi-objective, but let me tell you. So single objective means that what function we need to optimize. And in move situation, multi-objective optimization function. So how the multi-objective optimization problems are solved now in the present approaches? In the present approaches, move is mostly solved using MOO, multi-objective optimization, is solved using the soft computing and genetic algorithms. So what is the problem there? Because they are too much complex in nature. So it takes a huge time to solve these problems. Now with help of quantum computing, we think that we can solve these genetic algorithms or any move problem, the multi-objective optimization problem. So let me give you one such example of the multi-objective optimization problem. Say you are sitting in a steel plant where you need to find that your target is to reduce the silicon precipitation. In a steel plant, if the silicon precipitation crosses the 1.2% of the total steel, immediately the blast furnace can blast. The furnace can blast, which will impact in the serious health hazard for the employees there. And that's why they need to check that what is the silicon level. Now, for the silicon precipitation identification, I mean, the silicon can now come from the three sources. One source is the slag, one from the coal, one from the iron ore. Now, you need to make a optimal steel with proper blending of these three things, the coal, slag, and the iron ore. And silica source is, I mean, silica is coming from these three ores only. So you have to make an optimization with a goal that this one should be less than this. The target is that the silicon precipitation should be less than 1.2, but you have to optimize on these three. So we have to optimize the flow of coal, optimize the flow of iron core, optimize the flow of the other one also. So these are the typical multi-objective functions in nature, what will be benefited in the quantum optimization. Next one is the parameterized quantum circuit, are adjustable parameters to optimize quantum computations for machine learning tasks. So we can adjust the parameters, means the circuits itself are there where we can adjust the parameters. Like one simple example I mentioned that I want to, I found some data which is following say beta distribution or gamma distribution or maybe the Poisson distribution. I can adjust the parameters to get the similar data. Quantum neural network. Quantum neural network include CNN, convolutional recurrent RNN type RNN, generative adversarial network GAN, and autoencoder models utilizing quantum computing. So all these type of neural networks, CNN, RNN, GAN, and autoencoders, all are to be moved to something else. Utpal Ghosh, do you have any question? No, fine. I'm taking just one small, drinks break. I need to drink some water. Quantum optimization problems and hybrid models. So, quantum approximate optimization algorithm, we also known as the QA, or CAWA. In US, people love to speak it like this. That
Sir, one question has been raised. Sir, one question has been raised by one participant, that quantum computing complexity all NP hard problem.
Quantum computing can solve the problems of the NP hard problems also. Means NP is the non-polynomial. So not Ranjita Chaudhary, thanks for the question. So question is that classical computers, it takes a huge time to solve the NP hard problems, or we sometimes tell it is a not solvable in NP hard problems. But many of the NP hard problems can be solved using quantum computers. Okay, I'm coming to this slide now. So CAWA means the QA-OA finds approximate solutions to combinatorial optimization problems using parameterized quantum circuits. So I'm speaking so many times about the quantum circuit. What is quantum circuit? I mentioned that we can adjust that the parameters in the quantum circuit itself. Sorry. So this is that. Now coming to the variational autoencoder, you heard about the variational autoencoder. So here I'm writing that variational QE, VQE, eigensolver. So you know possibly that eigenvalues and eigenvectors are identified for the principal component analysis. So VQE is a hybrid quantum classical algorithm to find ground state energies of Hamiltonians efficiently. So Hamiltonians are the best, mathematical model found, based on it, lots of algorithms are developed. So here, that a VKV is the hybrid approach to find the ground state energies of the Hamiltonians efficiently. So this is one benefit. One is this quantum, QA-OA for this problem. And now for the annealing. So quantum annealing solves the optimization problems by evolving qubits from dual states to minimal energy configurations. So now coming to the neural network, quantum neural network basic. QNN use quantum circuits with feature maps and trainable to process classical inputs and produce outputs via measurements. So quantum neural network is a QNN, use quantum circuits with feature maps. Feature maps, you know that in, I mean, whatever we are doing using the neural network, and trainable analysis to process the classical inputs and produce outputs via measurements. Quantum convolutional QCNNs extend classical convolutional neural network with quantum convolutional and pooling layers. You can remember what pooling means, that the max pooling, soft max, these are the layers used for the CNN. So enabling efficient training on near-term quantum devices. So whatever the nearly available devices, people started to port the CNN in the quantum work. And I did some survey on it. I'll come at the end, maybe another 15 minutes I talk, and I'll come after that, maybe I talk about that how the CNN is, I mean, what is the performance of these different algorithms. Okay, I'll come to it. So convolutional, CNN is the convolutional neural network, is the convolutional, means quantum CNN, use quantum convolutional layers or pre-processing to enhance the feature extraction before classical. Means in CNN, what we do, that feature extraction is done in the CNN itself, and it is mentioned in the, I mean, deep learning books that starting from the very basic features, it reaches to the highest complex features. But one CNN uses quantum convolutional network so that it pre-process to enhance the feature extraction itself. So it is again somehow, it seems to me that we are going to the, I mean, previous age where the handwritten features were used for the neural networks. Next, quantum recurrent neural networks, QRNN, replace the classical RNN layers with structured parameterized quantum circuits for sequential data processing. I mean, you can recall that recursive neural network, one layer's feedback is coming to the below layer. So here, QRNN replace the classical RNN layers with structured parameterized quantum circuits. I mentioned what is the quantum circuits for the parameterized quantum circuits was when last slide I mentioned about it. Yeah, here I mentioned about the quantum parameterized quantum circuits. So this is something that we are using the parameterized quantum circuits for sequential data processing. Yes. So quantum kernel functions. Quantum kernels map n-dimensional inputs to higher m-dimensional space to enable advanced clustering and regression. So whenever we moved from, classically I can say in the 1980s, late 1970s possibly, that XOR problem was not solvable using classical neural networks. I think you can remember that what is exclusive OR? Exclusive OR is something that if it is 0, 0 or 1, 1, it has one value. And if it is 1, 0 or 0, 1, it has the other value. So it is not possible to draw a straight line in 2D to segregate both the classes. Okay. So for that, Ian Lekan, Hinton et al., they came out with the layer of that, the deep neural network came where even in 1995, Vapnik et al. Also presented the support vector machine where we tried to increase the dimension. And presently, in my day-to-day work, I am using autoencoder for this dimension reduction. So sorry, dimension increasing, so that we can get the better regression and the classification, clustering, anything you can say. That for how we are doing it, we are getting a data from time series. Using autoencoder, we are increasing the dimension to maybe 128 or 256. So similarly, quantum kernels map n-dimensional input. So if the input observation coming from n number of sensors, and you can treat each of the sensor as a dimension, means maybe one sensor data of itself can give 3 dimensions also, like the accelerometer. If you use the accelerometer, it gives the 3-dimensional data, x, y, and z acceleration across all these 3 directions it is giving. So now you see that using quantum machine learning, what we are doing is that we are using quantum kernels to map n-dimensional inputs to higher m-dimensional space, enable advanced clustering, because I mean it's already proved that if we can use autoencoders to increase the dimension, we can get better clustering and regressions. Now using quantum, we are doing the same thing, but here it is more efficient. With less complexity we can do it, means less time we can do it. Quantum clustering approaches. So I mean, I mentioned about so far the, machine learning. So clustering is another approach in classical. So quantum clustering uses quantum mechanics to find clusters by identifying density-based regions via Schrodinger's equation potentials. So it comes absolutely from the quantum mechanics principle, from the Schrodinger's equation, where you can just for Schrodinger's equation, I'm just trying to remind you the Schrodinger's cat, where it is something like that. If a single photon comes, if it is 0 or 1, if it is 1, it will trigger the it will trigger the rifle or the pistol, and the cat will die. So this is the quantum Schrodinger's equation. So now here you can see that earlier it was, density-based DB scan, density-based clustering. Here it is the quantum clustering is using the quantum mechanics to find the clusters by identifying density-based regions. Now density-based regions are coming from pure statistical. So from statistics to remove the Schrodinger sequence potentials. Anyway, Schrodinger's equation also uses lots of statistics and probability statistics and the integral calculus. So I'm not going to the debate. So here is the quantum clustering approaches. Quantum data in QML. Quantum data improves system states, Hamiltonians, and unitary transformations, and noise data from quantum machine learning tasks. Quantum data characteristics. Quantum data represents states and evolution of quantum systems governed by quantum mechanics principle. So here again, I'm repeating that we are moving from classical mechanics to the classical mechanics principle to the quantum mechanics principle in physics, almost 1,000, yeah, exactly 100 years back. So now we are moving from classical computing to quantum computing. If you see exactly 100 years back, what happened that in the same time of that 1925, so Rutherford, Niels Bohr, they are working. And after that, the Schrodinger's equation and everything came, maybe in the same time. So exactly some same manner, the machine learning was reigning. Now we are going to the quantum machine learning. Quantum data represent the states and evolutions of quantum systems governed by the quantum machine learning principles. Motivation for quantum datasets. High quality quantum datasets enable efficient quantum machine learning and accurate simulations of real-world systems. Right now, we really don't have high-quality quantum datasets for doing enough research. Data pre-processing importance. Pre-processing is absolutely important phase in machine learning. Pre-processing improves the data quality by cleaning, transforming and encoding data for quantum machine learning models also. So it's not like that pre-processing will be removed in the quantum. Pre-processing, the parameterizations and every step should be there. But for that, we need to search for quantum machine learning algorithms. Means quantum computing compatible pre-processing is a new area of research. Clustering, density-based clustering versus Schrodinger equation-based clustering. This is the transition what I can foresee, and possibly you can also foresee, and that's why you enlisted for that course. And if we can ready with all these things, we can very easily adopt the way which I am anticipating to come sometimes between 27 to 29 to 2030, maybe the full-fledged quantum machines would be there. Hybrid quantum preprocessing. Hybrid pipelines combine classical and quantum steps to maximize information extraction in quantum model development. Here comes the quantum data encoding techniques and their characteristics. I mentioned about the autoencoders or the, encoders, whatever you use in the classical machine learning, not classical, the deep learning algorithms also. In the classical computing, machine learning is using classical computing. Quantum data resides in Hilbert space, exhibiting superposition and entanglement properties essential for quantum computation. Here we are moving a significant from that Hadamard space to the Hilbert space. It's a significant transformation from the mathematical background is also required to migrate to these different paradigm of the computing itself. Overview of the quantum technique. Various quantum data encoding methods include basis, amplitude, angle, Q-sample, and QRAM encoding. Encoding implementations considerations include that encoding should minimize the qubit use and for efficient processing in current quantum devices. So diverse quantum data sets. So quantum data sets include 1-qubit systems, organic molecules, and spin models for varied research applications. So I mentioned about the 1-qubit, 2-qubit, and something I mentioned about maybe the other things, but organic molecules is something where, Shah Institute of Nuclear Physics of, India, in West Bengal to be specific, they are doing a lots of work on the organic molecules for the quantum computing. I have read some such papers who was earlier in US, now came here, is Professor Shangram. Professor Shangram, you can search some of his organic paper, or Shangram Bagh, yeah. Quantum circuit mapping datasets like mentally assist in solving circuit mapping problems using classification tasks for quantum devices. Quantum image classification, where I am working, I started with this, actually, you can remember the TensorFlow and PyTorch I mentioned. So TensorFlow quantum data uses, so TensorFlow quantum version is also available. Data uses qubits to encode pixel data, enabling quantum speedup in image classification. Right now, all the images are stored as a bits, and bits means even if you think of it as a color image, it everything is 3 byte, means that 3 byte is required for storing the red, green, and blue colors. Or if it is even the binary image, or the black and white image, then also 1 bit per pixel is required. What TensorFlow TFQ quantum data sets using that qubits to encode the pixel data, which speed up the image classification significantly. And benchmarking entangles datasets, benchmark quantum machine learning models with multi-portile entanglement and PQC inputs. So this is another how to benchmark the quantum models, because you are in the profession of teaching, so you are writing papers, I believe. So without benchmarking, no good papers are published. That's why I have added that one also. Quantum dataset types, tools, technologies, and hardware for quantum machine learning. So the last segment possibly. Quantum gate model. Quantum gate model uses reversible matrix operations on qubits to perform computations via quantum circuits. Quantum gate models is a reversible matrix, means reversible, something I also mentioned earlier, also reversible operations. So reversible matrix operations on qubits to perform computations via quantum circuits. Annular use quantum tunneling and superposition to find optimal solution for combinatorial problems. Combinatorial problems, you are all aware of the combinatoric issues. So it's a very time complexity is there to solve the the combinatorics problems using classical computing. Quantum hardware technologies, different qubit implementation use superconducting circuits, trapped ions, I mentioned earlier also, and photonic systems with varied advantages. Each of these have different advantages and disadvantages. And another one I missed here is that biomolecular, qubits. So this is something that Da Vinci, we all are aware of it. So Da Vinci Nonzo criteria mentions the defined necessary conditions for building scalable and functional quantum computers and communication systems. So this is the overview of the, Da Vinci's criteria. Superconducting qubits, macroscopic circuits manipulated by electromagnetic pulses, fundamentals to many quantum computers. Macroscopic circuits manipulated by the electromagnetic pulses. So electromagnetic pulses are manipulating the macroscopic circuits. So this is basic of many of the quantum computers. Trapped, I mentioned. So ions and neutral atoms manipulated by laser or light beams, offering long coherence times and scalability. So these all are the different quantum hardwares. Nothing is in place now, but how we are planning to, how we can see any of these things can be matured and we can get like spin and photonic qubits is also another approach. So these are the four approaches. Quantum circuit mappings and simulators, topological nanowire qubits. Majorana's qubit are stable topological particles promising fault-tolerant quantum, because I mentioned the one major limitation, stopping that quantum computers is that it's a very much noise, is very much, not that much noise resilient, or fault tolerance not that good. So this is something that these type of qubits are stable for the topological particles, promising fault-tolerant quantum computing. Quantum circuit mappings compiles quantum circuits to hardware representing qubits connectivity and reduces the gate errors. Quantum simulators emulate quantum systems on classical hardware, enabling noise and error analysis for the designs. Quantum primitives from programming building blocks, sorry for my throat. Managing noise and error scaling is crucial for the system growth. So these are something now key features for the quantum machine learning software tools. So if we think that any of these quantum hardwares, whatever I mentioned here, supporting this criteria, and these are the possible approaches of getting this hardware. Now, if it is available, how machine learning edge computing using quantum machine learning can be done. So IBM, now I'm taking one name, is the IBM QuizKit. QuizKit offers modules from machine learning, optimization, finance, and nature on IBM Quantum Cloud platform. So we all know that now from local computing to we move to the cloud era. Cloud era means where the three kings are here now. One is Microsoft, one is Google, and another is the Azure. So now from there, we are going to the QSKIT where cloud quantum is offered, is coming from IBM now. They are still doing monopoly. Other than some, yes, Zendao. Is this something the Chinese one? Pennylen supports quantum chemistry, machine learning, and quantum datasets with auto differentiation. Cloud computing platforms, cloud quantum computing platforms like QBread, IonQ Cloud, Amazon is in the business also. Microsoft Azure Quantum provides access to quantum hardwares and tools. I'm not sure whether they are using quantum inherently in the Azure Quantum Cloud or not, but it will give you the simulation results that even if it is not executed on a quantum, how much time it would take and what would be the accuracy on qubit instead of the normal base. community and learning, open source tools, emphasizing, because this is something absolutely important for people like me who are belonging to we are not that much attached with you people who are, I mean, every day possibly you are teaching to students, you are learning new things, but in industry, we are totally attached, I mean, detached a bit from the students. So open source tools emphasize the community engagement, tutorials, accessible learning, and strong research focus. And based on that, I mentioned about that Gartner report. So Gartner is giving something. Supporting infrastructure and cloud platforms. I'm taking some of the names here. You can take note, or anyway, I'll share the slide decks with you, but not in that format. I need to delete some of the materials from here and I'll share you the PDF file. Okay. So quantum resource management tools, these tools calculate logical and physical qubits and runtime to execute quantum applications efficiently. Cloud quantum computing platforms like Zepta, Orchestra, and Xanadu Cloud enables, I mean, every time I fail to pronounce it properly. So enable development and deployment of quantum and hybrid AI workflow. Molecular simulation for drug design, that is the most important area where we can foresee the usage of generative AI, and particularly generative AI for computing, quantum computing. We can see the first, I mean, most important, this, I mean, will come for the drug design and another for the genetic sequencing. So if genetic sequencing can be done, you know that lots of disease diagnosis and the healthcare domain itself will, I mean, it will be enormous revolution will come for the healthcare domain itself. So whenever I'm talking about the molecular drug design, right now, are you aware that how much time normally comes for the drug design? It takes for, I mean, nearly 5 to 10 years times it is coming for the new drugs. To synthesize new drugs, some lots of experiments are happening. I mean, needs to do, and then testing. Testing is a huge phase. Now, to fast track it, initially generative AI came for doing the drug design. Now, it is also time consuming in the classical computer. That's why Gen AI for molecular simulation for the drug design and executing on the cloud might be the first biggest disruption what we can see once the cloud computing comes and cloud machine learning, I mean, quantum machine learning will come. Quantum machine learning, quantum cloud, and quantum computers will be available. So quantum sensing applications. So this is something that that's now, I mean, I mentioned so far everything about the quantum computing. Now comes the quantum sensing. Quantum sensing detects atomic level changes in motion and electromagnetic fields for advanced technologies like GPS and the radars. Right now, whatever the decimal points, we can go beyond that. I mean, in the GPS, the accuracy is going to something layer, I mean, and the radars, every such systems, it will go to the highly accurate GPS and radar we can get if we use the quantum sensing, because it's tried to change the atomic layer things. So major cloud, I mean, quantum cloud services, I'm again repeating the cloud. So quantum cloud services, what are the features and benefits? Quantum cloud services enable development, simulations, and execution of quantum applications across various hardwares and classical integrations. So one set of business will emerge like IT companies today. You know, when I joined in a service company long back, that time one major work is to that moving from that, classical computing, I mean, so the what they used to say it, I'm forgetting that, COBOL and all these codes, to converting it to the new domain. And then I have also witnessed that migrating those data to cloud. Now, this is something that quantum cloud services enable development, simulation, and execution of quantum applications across various hardware and classical integrations. So right now, lots of systems are already developed using classical systems and classical machine learning. How we can take them without disrupting the production is a really big challenge. And this would be the future jobs where many people need to work on. Very simple example, I can say that how Y2K problem was solved, and that was the beginning of the, hype, boom of that, IT. So similarly, quantum integration, quantum transition from that, classical to quantum would be some future, and again, from cloud to quantum cloud. Drug design, I spent lots of time earlier. So now Gen AI. Platforms like Zapata, Orchestra allow rapid prototyping with execution of Gen AI applications on hybrid quantum classical systems. So for all these things, you need to burn your hands. Unless you start looking at it and do some experiment on that, how it is generative AI is everyone is speaking now. Even now, people are moving from classical system, they're trying to adapt generative AI. Maybe 5 years down the line, another disruption will come where people need to move from, generative AI to quantum generative AI. And these platforms will play a very important role that time. And quantum sensing, I mentioned that, it's a very emerging area. Some of the slides, actually, some copy-paste errors were there. Sorry for that.
So there is a query from the audience from Abira Bhattacharya. Which algorithm of QML are used to do drug designing and drug discovery?
It is not single. Thank you, Professor Abira, or I believe his faculty. So his faculty. So, not a single. So, for that, I suggest you to find the state of the art. I exactly cannot remember which one is the latest, but if you ask me, I can search it and give it to answer. Maybe, you can connect me in LinkedIn and I'll give you the exactly what all are there. So it is not a single one. I have found several algorithms, quantum machine learning algorithms, what are used for drug designing and not drug discovery. Something like, I can take it like that it is something that whatever, I'm just switching off the chat, sorry, a second. So whatever you can see the generative AI, so some of the generative AI algorithms are supported in the quantum cloud, be it by Microsoft, be it by Amazon, or be it by Zapata. Some algorithms are there for the generative AI, which are used for this. I exactly cannot say pinpoint that this is the best one. Molecular simulation. Coming to that same, whatever the questions was there. So some more points are coming here. And I mentioned it's a research and development is happening here. Quantum computers simulate molecular structures and behaviors more accurately than the classical computers, aiding drug discovery. At the same time, it is creating a new impact in the material science. Discovering of the new materials, new type of materials, people are working on it. And one more area I can tell you is in CERN, where how the world has been created. That discovery is, in CERN, all the researches are happening there. They are also using these things there are a huge amount of data to process them, they is using. Drug development efficiency, predictive quantum models filter promising drug candidates early, saving time and resource in the research and development. Yeah, I mentioned that is Zapata Orchestra, and this is that cloud enable rapid prototyping and execution of quantum drug design. So I exactly cannot, Abira, Professor, I don't know, Abira, I cannot tell you the answer that what is the algorithm, but for sure I know that some services are available in these two clouds where people are using it for discovery. What is inside this Zapata and Xanadu, I don't know. Quantum sensing and its impact on the various. So I started with that assumption that I'll not speak more on that cryptography. So industrial applications, quantum sensing improve the precision in manufacturing, civil engineering, environmental monitoring, and cosmic wave detection. I just in the last slide, I was talking about something CERN is using for this cosmic wave detection and for the cosmic, things they are doing. Possibly you have noticed that maybe a few days back, or maybe, I exactly can, maybe 1 month back also, some new planet was also identified. I don't know whether it be planet or not. After Neptune. After Neptune, there is a planet. Some people I exactly cannot remember the name. What that re, I mean that I mean that evolves around sun in 4,000 years. So when it came last time, possibly that time pyramids were there, something like that. During that time, when the pyramids were built, that time it witnessed, and it again comes to, in the orbit, what is now visible. Biomedical and meteorological uses, quantum sensors enable advanced in biomedical imaging and precise measurement for the meteorology. So meteorology is another area where the storm, thunderstorm, or the earthquake, people are trying to even earthquake from tsunami. Lots of, earthquakes are happening, below the sea. Now they're trying to use, using this computing, can we predict the earthquake also? Quantum cryptography, I told that I'm not going there. So quantum computing boosts the financial data modeling, risk management, credit risk is a absolutely important area in the banking and finance, and investment optimization, the better outcomes. Is there any proper session happen on the quantum cryptography? Otherwise, this is the last one. Otherwise, I'll skip it. Can someone please confirm? Is there any proper session on the quantum cryptography done?
Yes, the first session was on
I
quantum
know.
cryptography,
That's why
quantum key distribution actually.
this is
And there,
very much theoretical, I believe. So
yes,
application-wise, why the risk, I believe that was described. So I'm not
no,
going there.
no, no, no application has not been described.
Not at all. Okay. So
No.
then I have to. So you know that let me come from here. Okay. So I do the other way. For the financial things, just whenever you are trying to log into your, online banking, it's a two-way authentication. So it's a very common thing that Bob and something, two people are there. So some key is given to public key, private key, all these things were discussed. But what is the challenge in quantum? Now it is assumed that even if someone gets the OTP given to you, they cannot crack the other password, or if someone can crack the password, they cannot get the OTP within that 1 minute or 2 minutes of time. Because whenever you are getting the OTP in your mobile, you see that it is written that the OTP is valid for maybe next 2 minutes, 3 minutes at most. Some more question came here. Okay, there's a feedback path, not for me. Okay, Abira, okay, you are a PG scholar. Great. So that's why you are that much inquisitive. Thanks for your inquisitiveness. Okay, so here you see that so entire thing is relying on that even if someone gets the key or the OTP, they cannot break it within this time. Now, I told that with the quantum qubit, the classical image classification, very complex problem, can be solved within a few fraction of second. So that 1 minute or 2 minute criteria is broken. That is why quantum cryptography is a big challenge. So now quantum computing is, sorry, it was in the last slide. So sorry, here. So now coming here, the financial modeling. Yes. So financial modeling, where is the security one? Yes. So quantum sensors provide unprecedented precisions and spatial resolutions for application like quantum cryptography, security, financial modeling. Yes. Now, quantum computing enhances the investment gains, reduces capital needs, and improves risk and compliance management. Two use cases I can readily, explain here. One is the share price prediction. You know that whoever are in the business of share trading, even if not in share trading, if you are investing in the mutual fund, on behalf of you, it's ultimately your money is going to, even you are investing in mutual fund, your money is going to the share market itself. they are using this type of models now to very fast getting that what would be the trend. So if we use something and I get the trend maybe after 3:30, and when the share market is closed, I cannot take any decision. Logistic optimization challenges. Quantum computing offers solution to complex logistic issues like air traffic routing and supply chain disruptions. I have mentioned about the port. I mean, how the port management is done and how we are thinking something changes in the disruption in the port. Possibly you have seen that the Vizinam port is something came recently in the Kerala with help of Kerala government and our group, means Adani group, it came. So we are doing some logistic optimizations for the ports and airports also, but we are not yet using quantum, but we have a roadmap that we can use quantum in future. ESG, sustainability is absolutely important factor. Quantum tech supports sustainable energy solutions and reduces the energy waste. The main reason behind is that if we can compute very fast and we can store big data, automatically the e-wastage reduces significantly. And it definitely helps the environment, social and governance goals. So carbon neutrality is something the organization goals for many of the corporates is already we got the goals for the carbon neutrality. So this is something we can foresee as a environmental sustainable goals. With these, I am concluding that interdisciplinary field, it is a something where mathematics, physics, apart from computer, electrical, electronics, uh, basic physics, basic mathematics, basic chemistry, and drug means the biomedical, everything will be benefited by these. So here, AI to AI to solve the complex problems and innovative approaches. It is built on core concepts from the quantum mechanics. That's why I mentioned that physics will be again, I mean, some physics graduates will be again, maybe take some leads for, I mean, doing this. Transformative applications, quantum machine learning advances applications across verified fields, enabling new technological breakthroughs. With this at 8:52, I'm saying you thank you. And if you have any questions, I try to take the questions in between itself. I'll try to answer. I cannot ensure that I have all the answers because so fast the field is emerging. Any questions?
Participant, you can ask sir your question through the chat, or you can unmute yourself and then ask.
I'm trying to switch on my video because I stopped the presentation so that you can see me now.
Participants are requested to ask their queries if they have any query.
At least some questions came. That means
Yes,
they
sir.
were not using mobile during this online sessions. Really, online sessions is really, I'm scared that how many people are really listening or not. But thanks, Abira, Ranjita, for your questions.
So with this, we come to the end of today's session. Sir, thanks a lot. You have discussed very nicely and with simple words. You have explained and you also showed us the references from where we can study about
I'm
this
sharing it also.
emerging topic.
Not only have shared, I'm sharing it also for you. Yeah, in
Yes,
the
sir.
chat
Yes,
thread.
sir.
Okay.
Yes, sir. Thanks a lot, sir. Uh, thank you. Thank you, sir.
Yeah, I have shared it. So you, whoever are there, you can download it. Survey on the quantum machine learning. Okay.
There is
What
a
One
question in the
question
chat
is
are
there.
the
section.
most
One
used?
question is there,
I
sir.
got it. What are the most used optimization algorithms used in quantum computing? Again, I am using the cloud services, so I don't know the exact algorithm. But if you ask me, if you want the answer, I can search and I can get back to you. Maybe in future, maybe. I mean, tomorrow itself I can go. I mean, get back to you. You can connect me in LinkedIn for any more
So there
queries.
is another question, sir. What is
Sir,
your thoughts on quantum NLP from
yes,
Shayon?
I will Shayonde, I mean, I covered NLP as a part of generative AI. because most of the, I mean, NLP is now is pronounced as the, I mean, as a generative AI. So whatever I mentioned about the generative AI is the, I mean, you can treat it synonymously for that. I mean, large language model, small language model, whatever I mentioned all through my presentation is everything for the quantum NLP.
Hello.
Yeah.
Yes, sir. Am I audible?
Yes.
Sir, actually, I am not belong from that field, but it was an excellent session and came to know different things regarding the
Sir,
quantum.
can
Because,
you please tell your name first?
yeah, sir, this is Rajesh Mukherjee from Holding Institute of Technology.
Thank you.
Okay.
And, sir, basically, first of all, thank you because this is entirely new things for me and have learned lots of things. And
Thank you.
really, it's a kind of thing that is just recently explored to me throughout your speech. So,
You are
sir,
from
I was
which
just
university?
from Holding Institute of Technology.
Okay, I'm supposed to go there tomorrow, but I had to cancel it because I'm in Ahmedabad.
Okay, sir. Okay. So, sir, my question is that yeah, I am in this particular things, quantum field and quantum entanglement, recent advancement. I am listening and reading many of the posts and blogs, though I haven't used in my day-to-day research work. But sir,
Exactly.
my question is little bit different than your subject today, what you are delivered. I found very much fascinating things about the quantum entanglement, and what comes after that, that is yet to be very much tough for me to understand whether it is feasible or not. I recently find certain post certain blog from certain scientists, they are also connecting those things with tremendous kind of things. For example, that the entanglement, that if you observe a particular part and it will be filled to the other part, that they are reflecting with a kind of mother child relationship kind of things. That science fiction story, that blog I am also reading. And
Yes. So
the
I
people
can
who
tell
are
you,
writing it, I cannot ignore it because they also have very
no,
tremendous
no,
background.
it's very
So
much,
what
very much
what is
important.
your thought?
Yeah, yeah. I mean, I am very, very, what I can say that I'm pure industry person. I'm reading also. So what I can quote from Professor Geoffrey Hinton. So I'm trailing myself as a thought leader because I'm reading more paper, nothing else. So, and I know that whose paper is more, I mean, important. So Professor Hinton recently made a very important comment. So with the advancement of AI and particularly quantum AI, Hinton made a comment. I mean, Professor Hinton, just Jeffrey Hinton, let me take a few times because I am really privileged to, I mean, attend him in person in 2018 in Montreal. So he is the Turing Award winner 2018 and Nobel Physics 2024. And his grandfather was George Boole, who is founder of the Boolean algebra. So let me tell about, I mean, Geoffrey Hinton first to establish the credibility. My take on Geoffrey Hinton told that whenever some intelligent system came, it ultimately rules the world. So the target of the AI professionals in future should be something like that. AI should be treated as a being a mother and human being as their children so that they can never do any harm for their children. This is the comment from Hinton. So that is the only, I mean, I can iterate from his words only.
Thank you, sir. Thank you, sir.
So
So
there is
there is
another
another
question, sir.
question in the chat
Other
Yes,
section.
question,
yes, I
sir.
can read it. So said, just like agentic AI now, shall we expect quantum agents with quantum LLM? I'm sorry to say that agentic AI is again already, I mean, Shayan again. So Professor Joshua Bengio published one paper in 2025, 24th of February, Scientist AI, where he shown that agentic AI will be using the very malpractices to I mean to I mean politically biased and all these things can happen, the agentic AIs. That's why he thought about the scientist AI. So now future is definitely quantum LLM is not future. People started to use quantum LLM. Quantum scientist AI would be the future, in my opinion, where some like what I was discussing with in the last, I mean, with someone from Holdi, I'm forgetting his name. So what I was discussing that now quantum will behave like a scientist that this is good student, this is bad student. Means this agent is good, this agent is bad. And all agents are again quantum agents, quantum machine learning agents. So that is something that, I mean, hurts future wherever we are heading towards. It
Is there any
sometimes,
more question?
yeah, Shayan, really sounds like that science fiction stories. I'm really happy that even taking an online session, so much questions is coming. It's already
Yes, yes,
9
sir.
p.m.
Yes, sir. So, along with thanking you, sir, we thank the participants to actively participate in this
Tamasha,
session.
no, Tamasha, one more question.
Yes,
Tamasha
yes, yes,
Chakraborty,
sir.
no Tamasha. So quantum will not act like scientist. Quantum machine learning will act like scientist. Means scientist AI, I mean, hosted on quantum machine learning will serve this purpose. Okay. Okay. Thank you. Can I leave now?
Yes, sir. Thanks again, sir, for answering all the doubts and queries. And thanks a lot for such a nice session, sir. Thanks a lot, sir.
Yeah,
Thank
I
you.
mean, my reference papers have been already given. So is it that something
Yes, sir.
certificates? No,
Sir,
no. Thank
we'll
you.
get we'll get back to you, sir, for this
Sure, sure.
purpose.
Please,
Yes, sir.
please.
Yes, sir.
Bye.
Yeah.
I'm leaving.
We'll communicate.
Sir,
Bye.
Okay, sir. Okay,
will
sir.
you please send the PPT?
Yeah, I mean, can I share to Shoma ma'am?
Yes, you can share.
Can you share
I will share to participants.
in the same, no, auto faculty development is something that, no. I mean, can you
No,
drop a mail to my office, I mean, office site? It's a tanushyam.chattopadhya@adani.com.
I am sending mail that
Please
way.
share it so that I can immediately share it with you.
Okay.
Okay.
Okay, sir. Thank you, sir.
I shared my reference itself, so why not the slide? So people avoid to sharing the slides and the
Yes,
references.
sir.
Yes,
Yes,
everything
sir.
is open for me.
Okay, sir.
Okay, thank you. Bye.
Thank you, sir. Thank you, sir. Good night, sir.
Okay, thank you, participants. I'm going to close the meeting
PD sir,
now.
PD sir,
Hmm, hmm.
if anyone left to give the feedback, please ask them because only 52 feedback we have received till now.
The present participants are asked if you didn't the feedback, do it immediately. It is available in chat section.
Someone is asking for the feedback form.
Yes, feedback form again. Participants are requested to fill up the form.